All right, today we're diving into a classic computer science showdown, adjacency matrix versus adjacency list. This isn't just a boring technical comparison, folks. We're talking about a head-to-head battle between two totally fundamental ways to represent networks in your code.
So let me ask you this. Have you ever been in that spot where you've written this, brilliant piece of code, but it just crawls? It's so slow. Well, a lot of the time, the real culprit isn't your algorithm's logic. It's something way more fundamental, the data structure you picked. And believe me, that choice can have massive consequences for performance.
I mean, think about it. At the heart of everything, from social media to Google Maps, there's this single crucial choice. How do you actually store the connections? Before any algorithm can find the shortest path or recommend a friend on Facebook, it has to understand the network first. And that really gets to the core of our problem today. How do we efficiently tell a computer which nodes are connected to which?
Okay, let's meet our first contender. In this corner, we have the adjacency matrix. You can think of this one as the heavyweight champion of structure and predictability. It's powerful, it's kind of rigid, and it leaves absolutely no room for ambiguity.
So, what is it exactly? Well, just imagine a big grid, kind of like a spreadsheet. The rows and the columns, those are all the nodes in your graph. Now, if node I is connected to node J, you just pop a 1 in that cell. If they're not connected, it's a 0. It's really that simple. Oh, and if you have weighted graphs, you just store the weight of the edge instead of a 1. Easy.
I love this analogy. It's like a full calendar with every single possible time slot visible. This really captures the whole idea of the matrix. You can instantly check any specific box. Is there a meeting at 3 p.m. on Tuesday? But most of those boxes might be totally empty. Every possible connection gets its own dedicated spot in memory, which means you can check for an edge instantly. But, and this is a big but, that speed comes at a cost. You're often storing a lot of empty space.
All right, now for a completely different approach. Let's bring out our second contender, the adjacency list. If the matrix was the heavyweight, this is the nimble, efficient, and super flexible challenger. It's designed for a world where, not everything is connected to everything else.
So instead of that giant grid that maps out every single possibility, the adjacency list takes a way more direct approach. For each node, you just keep a simple little list of the other nodes it's actually connected to. That's it. No more, no less.
And the analogy here is just perfect. It's like your phone's contact list, right? You don't have an entry for every single person on the planet, do you? No, you just have the people you actually know. That is exactly how an adjacency list works. It's compact, it's quick to scroll through, and it only stores the connections that truly exist.
Okay, we've met our two contenders. Now, it is time for the main event, the performance showdown. We're going to break down exactly how these two stack up by the numbers when it comes to the things that really matter: space, speed, and efficiency. Let's get into it.
And here it is, the tail of the tape. This table right here is the key to understanding the entire trade-off. Now, we're using big O notation to measure performance. Just remember two things. N is the number of nodes, or vertices, and M is the number of actual connections, or edges. And right away, you can see some huge differences. Look at how they handle space, check for edges, and find neighbors. So let's break down what each of these rows really means.
Okay, round one, space usage. The matrix takes O of n squared space, period. It always has to allocate a spot for every single possible edge, whether it exists or not. The list, on the other hand, only takes O of m plus m space. Its size is proportional to what's actually there. So for what we call a sparse graph, think of a road map, where cities only have a few connecting roads. The list is a massive winner when it comes to saving memory.
Now for round two, checking if an edge exists. And let me tell you, this is the matrix's knockout punch. It's a guaranteed O of 1 operation. That means a single instantaneous lookup. The list, if you implement it well with something like a hash set, is usually just as fast. It has an expected time of O of 1. But that word expected means that in some very rare cases, it could be slower. So for pure, guaranteed, constant time speed on this one specific task, the matrix absolutely takes the round.
But this next round, this one is often the decider. Round 3, finding all of a node's neighbors. To do this, the matrix has to scan an entire row of n items, even if that node only has one single neighbor. The list, however, is perfectly efficient here. It just hands you its list of neighbors, which takes time proportional to how many neighbors there actually are. For common algorithms like breadth first search or Dijkstra's, which are doing this constantly, This difference is an absolute game changer.
So, after 3 rounds, who's our winner? Well, the truth is, there isn't one single champion. The right choice depends entirely on the fight you're in. So let's get to the final verdict so you know exactly how to choose your champion for your specific problem.
Here are the rules of thumb. It's all about knowing when to use which. You are going to reach for the adjacency list for most real-world situations, things like social networks or maps where graphs are sparse. If your algorithm is all about traversal, like finding a route in Google Maps, the list is your champion, hands down. But you'll want the adjacency matrix for what we call dense graphs, where almost every node is connected to every other node. And if you absolutely need that guaranteed constant time edge check, or you're doing some heavy-duty linear algebra with your graph, then the matrix is the heavyweight you need in your corner.
And there you have it. The showdown is over. Now you know the trade-offs, and you're equipped to make a really informed choice. So the next time you're building a system with a network at its core, you'll know exactly which tool to reach for. The only question left is, what will you choose for your next project?